In this talk, I will be presenting my project on a learning-based framework for self-driven design of networking protocols. To begin with, let's look at a very recent forecast by the International Data Corporation, which estimates that there will be 41.6 billion connected wireless devices in 2025. When designing protocols for such a wide range of heterogeneous devices, protocol designers should consider the device constraint and also the user objectives such as higher throughput, lower latency, lower energy consumption, as well as the network condition and the application requirements that run on top of these devices. All this together makes the protocol design a very complex and time-consuming process. Therefore, varying application requirements, user objectives, and frequent changes in the network condition can lead to tricky scenarios. Using all the protocol functionalities under all the scenarios is non-optimal and can add significant extra overhead in terms of latency and bandwidth. So, the objective of this project is to have protocols that could intelligently adapt to network conditions, application requirements, and user objectives. In this project, we focus on the wireless medium access control protocol. But what is a protocol? In simple terms, a protocol is an established set of predefined rules that determine how data is transmitted between different devices, which consist of a set of main functionalities. As an example, in the right figure, you can see a Wi-Fi MAC protocol in which the main functionalities are highlighted in orange. For example, here if the two phones want to talk to each other through the Wi-Fi router, they need to follow the predefined rules as depicted in the figure. However, depending on the network condition and configuration, not all the functionalities are optimal and can add extra overhead. To achieve our objective, we perform two main steps. First, we decouple a protocol into its main functionalities, and from now on we refer them as building blocks. In the second step, we design a deep reinforcement learning-based agent that learns to select the best set of building blocks based on the network condition and configuration. But how the agent learns? Simply put, the agent learns by interacting with the environment. To implement our DRL agent, we adopted Deep Q network, which is based on Q-learning, that is a popular reinforcement learning algorithm. For the sake of time, we're going to explain how we map DeepQN for our problem and leave the details behind. So, in every reinforcement learning algorithm, there are three things that are important: the state, the action, and the reward. So, based on the observed state, the agent is going to take an action in the environment and receives a reward for that action. In our problem, we define the state as the history of the channel state, like the Wi-Fi channel, whether the channel is idle, whether the packet that was sent was successful or it was collided, as well as the selected previous blocks by the agent and the number of nodes. The action is to choose one of the combinations of the building blocks, and the reward is the throughput. To evaluate our proposed framework, we implemented a Wi-Fi simulator using C++ with more than 10,000 lines of code. We also implemented the DQN agent using TensorFlow. We evaluated the DRL agent under 8 different scenarios in terms of convergence rate, the adaptability to the network condition, and the throughput gain compared to the conventional networking protocols. We also implemented and evaluated some of the MAC functionalities on commodity routers and desktops. For the sake of time, we present some of the results here and leave the rest. In these graphs, we compare the adaptability and the throughput of our DRL agent, which we call DeepMAC here, with the conventional CSMA-CA protocol that has been used in Wi-Fi. So as we can see, when the number of nodes increases, DeepMAC throughput is maintained. On the contrary, CSMA-CA protocol's throughput drops. Even when the network is saturated with more number of nodes as 50, DeepMAC's throughput is still higher than CSMA-CA. So, to show what blocks are selected by DeepMAC, as we can see for scenarios when the network load is low, meaning we have lower number of nodes in the network, DeepMAC tries to eliminate the control packets such as ACK and backoff in order to increase the throughput and decrease the overhead. On the other hand, when The load goes high, Big Mac keeps control packets in order to avoid collisions, which is very smart. The impact and moving forward. The proposed framework could revolutionize traditional protocol design process since it could be used as a blueprint for protocols across all the network stack. It can also help saving valuable human resources and time. It gives better insights about the protocol design to the expert, and it can also lead to more robust protocols as we've seen in the results. Moving forward, we'll be using GNN to capture the relation between the protocol building blocks to automate the validation of them. And we would be also developing a pool of blocks of different protocols to be used by the research community for advancing machine learning and networking field together. Thank you for listening to my talk.